Hello! In this video, we will consider our third and final trigonometric substitution, namely x equals a secant of theta. This particular trig substitution is used when we have an integral containing an odd power of the square root of x squared minus a squared. So in this video, we'll look at an example demonstrating how to perform this substitution and integrate and then complete the back substitution. Suppose we have the following integrals. In each of these integrals, we see that we have a power of the square root of x squared minus a squared, although we might use a variable other than x, and a is some constant. We have, like for instance, in this third integral, the integral of dz over z squared times the square root of z squared minus 49. Under the radical here, we have z squared minus 49, so this would be like our x squared minus a squared. So in this case, a is equal to 7. When we see a power of the square root of x squared minus a squared, we can apply the trigonometric substitution of the form x equals a secant of theta. And as you recall, secant of theta is equal to the length of the hypotenuse over the length of this side adjacent to angle theta. So I can draw a triangle, a reference triangle related to secant of theta equals the hypotenuse over the adjacent, and then we can use the Pythagorean theorem to find the length of the third side, namely the side opposite angle theta, which in this case is the square root of x squared minus a squared. So now when I consider the square root of x squared minus a squared and I use that substitution that x is equal to a secant of theta, I square a secant of theta, subtract a squared, under the square root sign, I've got a squared times the quantity secant squared theta minus 1. Under the radical, you'll recall the Pythagorean identity says that 1 plus tangent squared theta gives us secant squared theta. So in a similar way, secant squared theta minus 1 will give us tangent squared theta. In reality, this quantity in the square root of a squared times tangent squared theta will simplify to be the absolute value of a tangent of theta. And I want it in absolute value because when I'm taking the square root, I'm not going to get a negative, and I don't have a negative sign out in front. So I always want the positive value. So let's consider how we would work through the trig substitution with that first integral. First, we have to see that since we don't have a factor of w or even a multiple of w in the numerator, a u substitution really would not be helpful. It would not produce a simpler integral. So we will consider the trigonometric substitution. Specifically, we'll look at w squared minus 4 as being our w squared minus our a squared, so that a squared is equal to 4 and a is equal to 2. So we'll use w equals 2 secant of theta. We take the derivative of both sides and solve for dw and find that dw is equal to 2 secant of theta tangent of theta d theta. And now we return to our original integral and make a substitution for each w and for our differential dw. So dw is replaced with 2 secant theta tangent of theta d theta. W is replaced with 2 secant of theta. It gets squared. You subtract 4, and then that quantity is raised to the 3/2 power. So we have the integral of 2 secant theta tangent theta all over 4 secant squared theta minus 4 to the 3/2 power. I've got a factor of 4 in each term inside parentheses in the denominator. I can factor that out. And I can pull the 4 to the 3/2 power out in front within that denominator. And I have the integral of 2 secant theta tangent theta over 4 to the 3/2 power times the quantity secant squared theta minus 1 to the 3/2 power. We just recall that secant squared theta minus 1 gives us tangent squared theta, so we'll make a replacement there. We also can note that 2 over 4 to the 3/2 power can be simplified to be 1/4. And so we have 1/4 times the integral of secant theta tangent theta all over tangent squared theta to the 3/2 power. Next, we'll multiply those powers in the denominator. So we'll get a tangent cubed in the denominator, and then continue with some algebra to make things simpler. So we have that our integral 1 over w squared minus 4 to the 3/2 power dw is equal to 1/4 times the integral of secant theta over tangent squared theta d theta. Secant of theta is the same thing as 1 over cosine of theta. Tangent squared theta is sine squared theta over cosine squared theta, but it's in the denominator, so I can invert and multiply. So I have cosine squared theta over sine squared theta d theta. I can simplify things a little bit, and I'm going to be left with a cosine of theta over sine squared of theta. I could see that cosine of theta is actually the derivative of sine of theta. So I could do a u substitution with u being sine of theta and du is the cosine of theta, d theta. Or I could also see that this is the same thing as 1/4 times the integral of the cosine of theta over the sine of theta times 1 over sine of theta, d theta. Which I can see that that integral is then the same thing as 1/4 times the integral of cosecant of theta, cotangent of theta, d theta. So if I recall my basic antiderivatives, what's a function whose derivative is cosecant theta, cotangent theta? I recall that that's just simply going to be negative cosecant of theta. So I multiply that times 1/4 and add my constant. I started with an integral in terms of w. I'm ending with an integral in terms of theta, so I have to do a back substitution. Again, returning to the start of our substitution with w is equal to 2 secant of theta. So secant of theta is equal to w over 2. Secant of theta in a right triangle is hypotenuse over the adjacent. So I can label a triangle, use the Pythagorean theorem to complete the length of the third side, that side that's opposite theta. I need cosecant of theta, and cosecant of theta is the hypotenuse over the opposite. So it's the length of the hypotenuse over the length of the opposite side. I make that replacement, and I get that my integral is negative 1/4 w over the square root of w squared minus 4 plus c. As we have in the other videos, I'm asking you to verify that the derivative of our result, the derivative of negative 1/4 w over the square root of w squared minus 4 plus c, is in fact 1 over the quantity w squared minus 4 to the 3/2 power. And when you're finished with that, you can give your efforts to evaluating these two integrals. Again, checking to see if you can use u substitution before using any trig substitution. Or there might be another method yet that might be more helpful. And in summary, as we have with the other two videos on trig substitution, make sure that you consider the form of the integral and your known antiderivatives before pursuing a trigonometric substitution. There might be a method, whether it's u substitution or another method that will simplify the integral. You need to be sure to recognize the various quadratic forms associated with the trig substitutions and make sure that you substitute not only for the variable but also for the differential. And recall that the square root of x squared minus a squared means that the best trig substitution would be x equals a secant of theta, which means that the square root of a squared secant squared theta minus a squared would result in the absolute value of a tangent of theta. You want to simplify, then integrate, then complete the back substitution.